The focus of this video is correlation. I'll be previewing what it is and how it's used. The most commonly used form of correlation is called a bivariate correlation. As the name implies, a bivariate correlation looks at two variables to see if they are related. In a typical correlation, especially those used by beginners, both variables are quantitative. This means that each variable is being measured with a number representing quantity. Relationships are trends or connections between two quantitative variables, but we need to keep in mind that a relationship does not necessarily provide any evidence of causation. You may hear the phrase correlation does not equal causation. This is used to remind researchers that just because two things are related doesn't mean that one causes the other. The standard correlation formula is commonly known as the PPMC. This stands for Pearson Product Moment Correlation. Oftentimes when people say they're using a correlation and they don't specify, they're using this common formula, the PPMC. This formula summarizes the relationship between two quantitative variables by giving a number that ranges from -1 to +1. This value is known as R. The R value indicates two things about the relationship between two variables: the strength of the relationship and the direction of the relationship. The strength is how clearly or strongly the variables are related. The greater the R value in absolute value, the stronger the relationship. The weaker the R value, or the closer it is to 0, the weaker the correlation is between two variables. Direction refers to whether the variable trends are similar or dissimilar to one another. That means, do the two variables increase together? Or is it that when one increases, the other one tends to decrease? The direction of the relationship can either be positive or negative. Positive correlations are also known as direct correlations. In a positive correlation, when X increases, Y increases, and when X decreases, Y decreases. Notice that the two variables, which we're calling X and Y, are doing the same thing at the same time. When one goes up, the other goes up. When one goes down, the other goes down. In contrast, in a negative correlation, X and Y do opposite things. That means that when X increases, Y tends to decrease, and when X decreases, Y tends to increase. Correlations can be easily represented on a two-dimensional XY graph, where the X variable is plotted along the X-axis and the Y variable is plotted along the Y-axis. Increases on the X-axis are represented by movements going to the right, and increases on the Y-axis are indicated by movements going up. Take height and weight, for instance. Typically, folks who are shorter in height are also lower in weight, and folks who are greater in height tend to be greater in weight. And then we also see folks who are moderate who tend to be more moderate. The graph which is forming is known as a scatter plot, scatter dot graph, or scattergram. In a scatter plot, each dot represents one case which has been measured on X and Y. The coordinates of their X and Y score are plotted on the two-dimensional graph. Once all data have been collected and plotted, the researcher looks for a general trend. Here we see a pretty clear trend going from low with low to high with high. This is what's known as a positive trend or a positive correlation. We see that as height increases, weight also tends to increase, and as height decreases, weight also tends to decrease. Other variables could have a negative trend. Let's take a look at the example of exercise and stress. It may be that the more we exercise, the less stressed we feel, and the less we exercise, the more stressed we feel. In that case, our dots may look like this. In this example, folks who don't exercise much tend to have high stress, and those who do exercise a lot tend to have low stress. So we see that the direction of our trend is negative. Keep in mind here that the terms negative and positive are not moral or value judgments in statistics. Negative means that as X increases, Y decreases. hence the negative, whereas positive indicates that as x increases, y increases, hence the positive. The entire graph and the position of the dots summarized as r using the correlation formula. R can range from -1 to +1. It cannot go outside of these boundaries. When R is -1, it means there's a perfect negative correlation. Here's an example of what a graph could look like when R equals -1.00. Notice that the dots have a very clear straight line that they're moving in, where each time x increases, y decreases in the same fashion. When the trend is fairly clear but not perfect, then it's going to have a strength that's close to -1, but not exactly -1. Take a look at the trend here. Though we still have that clear straight line, not all the dots are staying perfectly in a row. We have to go a little bit wider to capture them all, but there's definitely a negative trend here. This is what our graph could look like if we had a fairly strong negative correlation of -0.80. As the dots get further from being a perfectly straight line, the correlation size gets smaller or closer to 0 in absolute value, meaning it's weaker or less clear. Notice here that if you're looking at the dots, you can still see a negative trend, but it's not nearly as obvious as when we were just looking at those ones that went down the center with no other dots obscuring that clear negative picture. As it gets even less clear, our correlation gets smaller. When there is no trend in the dots, that is, they look like a big cloud or a big mess, there's none of that clear angle going down or up as we move from left to right, then we have no relationship, indicated as r equals 0. Take a look at the dots now. I kind of see a positive trend going this way and a negative trend going that way, but those two cancel each other out. As overall, I'm just seeing a big blob of dots, not a clear line going consistently in one general direction. Whereas when r was equal to -1, the line was very clear. When r equals +1.00, it indicates the dots show a perfect positive correlation. Take a look at this example, where there's a clear trend of increase on x and y together. In this graph, r equals +1.00. But as dots move further away from the trend line, the trend gets weaker and weaker and weaker and weaker, until there's no clear trend and r once again is equal to 0. Now the dots can appear lots of different ways and still indicate -1, +1, or 0. We could have the three look like this, or possibly like this, or even like this. Notice that what's consistent among the negative correlations is that the dots are in a straight line. And in the positive correlation, that's perfect, they're also in a perfectly straight line. There's no correlation when we're seeing anything other than a trend approximating that line pointing either up from left to right or down from left to right. And notice these gaps that I've left in the graphs. That doesn't change the fact that there's clearly a line. Whereas in the middle one, I'm really seeing more of a circle shape, which isn't an indicator of a line at all. Now remember, I said this is for two variables. If either of the things you measured turns out to be a constant, you're going to get a non-interpretable graph because you cannot do a correlation when either of your variables is a constant. If your x turns out to be a constant instead of a variable, then you're going to end up with a perfectly vertical graph, like the one on the left. Whereas if y turns out to be a constant, you're going to get a perfectly horizontal graph, like the one here on the right. Notice that there is no slope to the lines because in the case of x being a constant, it's always the same number, so we've got a perfectly straight line pointing up. And when y is a constant, we have a perfectly straight line pointing from left to right. In order for two things to be correlated, we need to see some kind of slope. So in these two scenarios, it isn't even possible to compute a correlation. The strength of a correlation is interpreted using the absolute values of r. When r is equal to 1 or -1, the correlation is perfect. That's as strong as a correlation can be. When a correlation is between 0.8 and 0.99, or negative 0.8 and negative 0.99, it's considered very strong. In fact, 0.99 is so close to perfect that sometimes folks will interpret it as perfect given a little bit of rounding error. Correlations from 0.6 to about 0.79 are typically called strong. This also includes negative 0.6 to negative 0.79. Correlations between 0.4 and 0.59 are typically considered moderate, as are correlations between negative 0.4 and negative 0.59. Correlations from approximately 0.2 to 0.39 or negative 0.2 to negative 0.39 are considered weak. And finally, a correlation of 0 indicates no correlation, whereas above that up to about 0.19 or negative 0.19 is typically considered very weak. The thresholds used here are typical rules of thumb. That means they're not hard and fast rules that dictate where we can use terminology. So the high ends of each of these actually are often treated as the low end of the next. Instead of saying 0 to 0.19, folks will often say 0 to 0.2, from 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, and from 0.8 to 1. Therefore, if you had a correlation of 0.8, it's considered acceptable to call it strong or very strong because it's right at the border of these two rules of thumb. Similarly, a correlation of 0.4 can be called moderate or weak. Both of these are considered acceptable because it's right on the threshold between these two boundaries using the rules of thumb. Take a look at these 8 different correlation coefficients, also known as R. Indicate whether each one is positive or negative and give the strength. When R equals 0, there is no correlation. We have no direction to indicate when things are not correlated. Negative 1.00 has a strength that is perfect and a direction that is negative. A correlation coefficient of 0.85 is very strong and positive, whereas a correlation of 0.12 is very weak and positive. An R equal to negative 0.75 is strong and negative, and a correlation of 0.22 is weak and positive. A correlation coefficient of 1.55 is highly problematic. This is because you cannot have an R outside the bounds of negative 1 to 1. If ever you get a number like this, which is not possible using the formula, it means you must have made a calculation error somewhere. And finally, a correlation coefficient, or R, equal to negative 0.60 can be called moderate or strong, and it is negative. The strongest correlation we have here is the negative 1, and the weakest is theoretically the 0 because it's so weak that there's actually 0 correlation. Take a look at these 3 positive trends and indicate which one is strongest and which one is weakest. The strongest is the one in the middle because we see a perfectly straight line. What matters for strength is that the dots are approximating a perfectly straight line. That's more important than how dramatically the line is sloping upward. As long as there's at least a little bit of slope and the dots are in a straight line, that correlation is perfect. Whereas the weakest one here is the one all the way to the right with the scatter of dots where there isn't much of a clear line, and we have about as many dots far from the line, 6, as there are dots that seem to be forming a line towards the middle, which is 5. Now if you look at the first one, we also see some weakness here, but look at the fact that we have many more dots that are close to the line and fewer dots that are further from the line than the proportion or ratio of dots close and far in the third graph. In our middle graph, our strongest one, they're all perfectly in a line and there are no dots outside of that space. Try these 3. Which is strongest and which is weakest? The strongest is definitely the first one because even though we see gaps in the dots, they're still forming that straight line with no dots veering off from that line. Now for weakest, you could have chosen the third graph if your rationale is that you can't actually even have a correlation here. Typically in this version, we don't consider it weak for having a correlation of 0. We consider it not appropriate for correlation. So the one that is the weakest here where a correlation is even possible is that middle graph, because that third graph, again, we would consider this as not being bivariate because there is a constant. So in summary, our strongest one is to the left, our weakest one where there's actually a correlation is to the middle, and the one where a correlation is not possible is the one to the right.